Hi guys, today we're going to look at Chapter 3, Derivatives, and I'd like you to read the chapter overview first on page 95. Before you do, I just want to mention that in section 3.1, we're going to be looking at the derivative of a function. We're going to define a derivative a couple of different ways. We're going to specifically work on notation and making sure that we have all the different notations and read it correctly. We'll look at the relationship between the graphs of f and f of x, or f prime is what we call that, and then we'll do the reverse. We'll look at the relationship between f prime and f. We'll graph the derivative from data, and we'll look at one-sided derivatives. So let's pause a minute and look at the overview on page 95. So let's start with the definition of derivative. The derivative of a function with respect to the variable x is the function f prime, and so when we look at that word there, or that notation there, we'll call it f prime, whose value at x is f prime of x is equal to the limit as h approaches 0. We have to still write that in there, f of x plus h minus f of x all over h. Now, the difference between what we've done before and what we're doing now is that the x is now, here is going to be an x, not an a, it could be a number. And we have to have provided the limit exists. So that's a key part of it, does the limit exist? So if f prime of x exists, that's here, we say that f has a derivative or is differentiable at x. And the function that is differentiable at every point of its domain is a differentiable function. So these words, differentiable, derivative, have meaning to where we're finding the slope of a tangent line. So let's start with this idea of taking the derivative of f of x equals x cubed, which means we're going to find the derivative. Now, this is a little bit long, but let's be patient with ourselves and multiplying things out. So the first thing we have to do is write our definition down. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So what we're going to do is wherever there is an x cubed, bring that back up, x cubed, then I'm going to replace it with x plus h quantity cubed minus x cubed. So maybe you don't remember how to multiply out x plus h cubed. You could do that the long way, x plus h times x plus h times x plus h. We know from Pascal's triangle that it's a 1, 3, 3, 1 triangle. So we have x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. So as we did before with our limits as h approached 0, is we simplify the numerator. So as you can see, the x cubes cancel out. And we distributed, we just took the minus, we factored out the h, which we see cancels out. And when we do, we get the limit as h approaches 0, which gives us 3x squared. So what we're seeing here is if f of x is equal to x cubed, its derivative is 3x squared. And right now we're going to continue to do it the long way, using the definition of derivative. Now there's an alternate definition that we want to look at. It's the derivative at a point. So they're actually giving us the value of A, or sometimes they'll just say at the point A. And if you notice, it's f of x minus f of A all over x minus A. So it is the slope formula, the change in y over the change in x. So let's apply that for this example. So we're going to say f prime of A is equal to the square root of x minus the square root of A all over x minus A. Oops. What did I forget? Let's go back. The limit as x goes to A. So in order to do this problem, what can we do? We had two methods of simplifying this. Our first method that we had was factoring, and then the other method that we had was to multiply by the conjugate. But we'd have to rationalize the numerator, not the denominator. So I'm going to choose to factor. So I'm going to write it as the limit as x approaches A of the square root of x minus the square root of A all over the square root of x minus the square root of A times the square root of x plus the square root of A. Do you agree that this denominator can be factored? We can simplify this. What we get is the limit as x approaches A of 1 over the square root of x plus the square root of A. And what we get is 1 over the square root of A plus the square root of A. Notice I'm not writing limit anymore because I'm substituting A into the x, and we get 1 over 2 square roots of A. So what would I say? If f of x is equal to the square root of x, then f prime of A is equal to 1 over the 2 square roots of A. Let's look at some notation for derivatives. So y prime is how we read the first one. We say y prime. So far we saw f prime of x, but we can also say y prime. We can say dy dx, or the derivative of y with respect to x. So whenever you see that notation, you would say the derivative of y with respect to x, or dy dx. We just say the dy dx. On the third one down, you would say df dx, or you would say the derivative of f with respect to x. And finally, we say d dx of f of x, or you can just say the derivative of f at x. Now, every one of these on the first three, along with f prime of x, has to be written before you write the derivative. However, in the last one, if they write it like this one, and the function is given, you can just put an equal sign and then give me the answer. So that's a different way of writing it. And we'll try to use a variety of ways that we write it over time so that you're familiar with all of them. Most people tend to like y prime and f prime of x. But what happens is that you start getting into differential equations that it's more convenient to write dy dx, or we use some other notation, and they're going to ask us questions in a variety of ways. So we need to become familiar with these. So our next idea today is slope. Here is the graph of f. It is in red. And I've already gotten my marks on it. You can see that I have here, it's a positive slope, a zero slope at -2. Then I have a negative slope. I'm putting all checks by it so you see what I'm talking about. A negative slope, and then I have a zero slope at 3.5. And then I go back to a positive slope and a positive slope. So our positive slopes are graphs of the derivative above the x-axis. When we do the derivative, we're going to graph it above the x-axis. A negative slope will be graphed of the derivative, we'll graph the derivative below the x-axis. Derivative will be below. And zero slopes will be graphed through the x-axis. Okay? So take a minute and graph this cubic. And our next slide will be the graph of the derivative. I think it's important you get this graph on your paper first, and this can be paused at any time, so you can get it copied. And then we will look at its graph, or of the derivative, and that's what we're going to be working on our worksheet today. So again, the positive, the slope will be above the x-axis, the negative slope will be below the x-axis. And the zero slopes will go through, the derivative will go through the x-axis. So let's look at the answer. Here is the graph of f prime of x. So notice that our zero slopes are located at -2 and 3.5. We see that all the positive slopes are above the axis. The negative slopes are below the axis, and then the positive slope is above the axis again. So what do you notice about the degree of f prime? Look at the graph. Tell your partner what that graph looks like. So we already know, because we did this earlier, that the function f of x was x cubed. And we learned that f prime of x from our first part, where we were taking the derivative using the definition, was 3x squared. So did you notice that this was a parabola? Maybe I don't have it drawn to scale. This is probably way lower. But that we have a derivative that is a 1 degree less. So let's go to page 98, the exploration. You're going to do that with your partner. When you're finished, you're going to check with your answers with the people in front or behind you to see if you have the same thing. You're going to mark which ones you have questions about. And finally, when you're finished that, you'll come up and get a worksheet, and you'll do numbers 1 through 10 in section 31. And that's all I have for you today.